Okay, so let's talk about exam question 1. So in the following figure, the horizontal surface on which this block slides is frictionless. If the two forces acting on it each have magnitudes of 30 newtons, and the mass of the block is 10 kilograms, what is the magnitude of the resulting acceleration of the block? So here, in the very first problem, we started off easy because we had the picture given to us to begin with. So we didn't have to start from scratch on the picture. We do want to definitely not neglect our other steps of our setup, of our mise en place. So first thing after we draw the picture, we want to make sure that we have our coordinates specified. And here we're going to have up be the positive y direction, and to the right will be the positive x direction. After we've got that taken care of, we want to write our vectors in component form. So we have two forces at work here, and one of them, which I'm going to label F1 here in the drawing, one of them is only horizontal. So the one that's only horizontal is easy to write down in vector form. It's got a magnitude of 30. It's all in the x direction, nothing in the y direction. The second force takes a little bit of work to break down, but if we note where the angle has been supplied, we know that the x portion of this vector is going to be associated with the cosine of 30. The y portion will be associated with sine of 30. So the x portion of this force is going to be 30 cosine 30 in the x direction, and it'll be minus 30 sine 30 in the y direction, where the minus sign comes from realizing that this force is going down into the right, and down is what we've defined as the negative y direction. Now that we have our mise en place out of the way, now we can actually start cooking. We're going to be using Newton's second law because, well, that's going to be our workhorse for the rest of the semester, actually. Now, we don't expect, in this case, for there to be any acceleration in the y direction. That is, we expect if you push on a block, it doesn't fly into the sky and it doesn't sink into the ground. So the acceleration we expect to see is something in the x direction. It's 0 in the y direction. In that case, we can really just analyze the x parts of Newton's second law. Where here we're going to add up the forces in the x direction, which is 30 plus 30 cosine 30, that equals 10a, where 10 is the mass here. Most of these things are just numbers at this point. So cosine of 30 is square root of 3 over 3. So we have 30 plus 30 square root of 3, square root of 3 over 2, I should say, equals 10a. Divide everything by 10, and we have 3 plus 3 square root 3 over 2 equals a. So there is the magnitude of the acceleration of our block. Any questions on this first problem? Everybody here's good with the explanation for problem number 1? Feel free to unmute yourself and speak up if you've got an issue. All right. Problem number 2. A mountain biker encounters a jump on a race course that sends him into the air at 60 degrees to the horizontal. If he lands at a point 45 meters horizontally to the right and 20 meters vertically below his launch point, what is his initial speed? So let's draw a picture. It's always our step 1. We've got some sort of jump. And at the end of the jump, of course we need to draw a mountain bike. Pretend that this is how mountain bikes look. We've got an initial velocity, 60 degrees to the horizontal. And we have a landing point down here. We know that the vertical distance from launch to landing is 20 meters. We know that the horizontal distance from launch to landing is 45 meters. And really, that's quite a jump. That's half a football field in American units. All right, so there's our picture. We're going to say that up is the positive y direction, to the right is the positive x direction, and that brings us to writing down our vectors in component form. The thing that we actually want to know is the initial speed, right? Whereas speed is the magnitude of velocity. So we would like to take our initial velocity and write it as some initial speed times a direction vector. Right, this is not very different than what we have done before, where we've said, well, if the hypotenuse is v naught, then the x part is v naught cosine theta, the y part is v naught sine theta. Here all I've done is factor out the v naught from taking it from inside the vector to outside the vector. The initial position of the jump, let's say that we are at 0 in the x direction, but we're 20 meters above the ground, which means that our final position is 45 meters to the right of where we started and 20 meters below. If we started at positive 20 meters, we ended at 0 meters. Note, it's also perfectly fine to say that the point of the launch is 0, 0. It's the origin. At that point, your landing point would just have the coordinates 45, negative 20. You're going to get exactly the same answer. So it doesn't actually matter where you choose your origin, as long as you just pick a spot and stick with it. Last thing we know is the acceleration, which is just going to be gravity. So we've got, we want to know something about initial velocity. We've got initial position, final position, acceleration. So if we take a look at our tools, that's going to look like our workhorse kinematic 2. So we're going to go ahead and write that down. Where our final position is equal to our initial position plus a displacement due to our initial velocity plus a displacement due to our acceleration. Now, if we take stock for a moment, we don't know what the initial speed is and we don't know what the time is. That's two unknowns. We need two equations to solve that. And fortunately, there are two equations inside this vector equation, one in the x direction and one in the y direction. So in the x direction, our initial position is 0. Our initial velocity is v naught cosine 60. And our initial acceleration is 0. In the y direction, also forgot to mention, we also know our final x position over here. So in the x direction, our final x position is going to be 45. In the y direction, our final position is going to be 0. Our initial position is going to be 20. Our initial velocity is v naught sine theta, or sine 60, sorry. And our acceleration is not 0, but is in fact gravity. You'll notice that I am rounding g from 9.81 to 10 because it is a Monday morning and I don't do decimals on Monday morning. So we have two equations, two unknowns. We can definitely solve for this. I mean, unfortunately, both unknowns are in both equations, so it doesn't actually matter where we start. We're going to have to do a full solve, substitute, solve again. In the x direction, we can simplify down to 45 equals v naught cosine 60 t. And if we solve for t, that becomes 45 over v naught cos 60. And I chose to solve for t instead of v naught because we don't actually care about time in this problem. So if we solve for t, substitute for t, t gets eliminated. We can solve for v naught. If we cared about t, we could do another substitution and solve for t again, but again, in this problem, we don't actually care about t. So, coming to the y equation, we're going to substitute in our expression for t that we got from considering the x direction. All right, we're going to do a little cleanup here. In our middle term here, notice that there's now a v naught in the numerator and denominator, so those cancel. There's a sine 60 over cosine 60, also known as tangent 60. So this middle term simplifies down to 45 tangent 60. And then our last term over here, we have minus 5 times 45 squared divided by v naught squared cosine squared 60. Going to give us a little bit of room to do this algebra. But we are in the home stretch at this point. We only have a v naught squared and not a v naught linear, so we don't have to use the quadratic equation, which is nice. So instead, I'm going to take this third term, add it to the left-hand side of the equation. And then we've got some junk attached to our v naught by multiplication, so I'm going to multiply or divide them off as appropriate, so that on the left-hand side we get 1 over v naught squared equals, we'll be dividing the whole thing by 45 squared, and dividing the whole thing by 5, and multiplying the whole thing by cosine squared. And lastly, we don't want 1 over v naught squared. We want just v naught. So I'm going to take the reciprocal of both sides and take the square root. Right, square root that whole thing there. Now this looks a little intimidating maybe, but everything in the brackets is a number. So it's actually really, really simple to deal with. We're going to plug everything into our calculator. Make sure that you're in degrees mode if you're using the measure of this angle as 60. And then we'll take the square root. And I find that the initial velocity is something like 20 meters a second, which is a fast but not unreasonably fast for a racing bike. We have any questions, any comments or questions on problem 2?
So, how far off would you count an answer for being correct?
I mean, anything between 19 and 21, I would say fine.
Okay.
Right? I don't do decimal points. I don't expect you guys to do decimal points most of the time. Like, significant figures are important when you're doing real engineering work, sure. In this class, they're going to be more of a rule of thumb. So if the numbers that go into a problem have like 2 or 3 significant figures, then your answer should probably have 2 or 3 significant figures. But I'm not going to make the effort to grade you on being off by a sig fig. That doesn't seem like a good use of anybody's time when you're learning physics for the first time. Does that answer your question?
Yeah, sort of. The only reason I was asking is somehow, I'm not sure how I did this, but I ended up getting like 26.
Oh.
And I don't know how. It's like close, but it's not there, and I'm not sure what I did to do that.
Well, the final answer is only worth 1 point on each problem. So I've been grading these on like a 10 points per problem sort of thing. You get 1 for having the right answer if you've done the work correctly, and the other 9 points are for doing the work correctly.
Okay. All right.
Any other questions before we move on? All right, let's talk about satellites. So a geosynchronous satellite has, by definition, an orbital period of 1 day, and it orbits at a distance of 42,250 kilometers from the center of the Earth. So what's the magnitude of its centripetal acceleration? So let's draw a nice picture. Here's the Earth, and way over here is a geosynchronous satellite. So most of the satellites that we use for internet or phone calls or GPS, they're orbiting like in here. they're in what we call low Earth orbit, right? A few hundred kilometers at most. But a geosynchronous orbit means that this satellite will always be pointing at the exact same patch of ground. And that means it has to orbit the Earth once per day so that it keeps in time with the Earth's rotation. So this here is really a unit conversion problem. We know a couple of things. We know that the centripetal acceleration of an object undergoing a circular motion is equal to v squared over r. Or we could also write that as omega squared times r. I'm going to use this second form here. Right, so we would like to know the angular speed of a geosynchronous satellite. And we would really like that unit to be in radians per second. So we're going to do a unit conversion. We want something in units of radians per second so that our units in our formula here work out. We've got something in units of like 1 rotation per day. So we need to do a couple steps of work here. You might know offhand that 1 day is equal to 86,400 seconds. If you don't, that's 60 seconds, right? If you don't remember that figure, and let's be honest, most people don't, we can do this in a few steps. We can say 1 day is equal to 24 hours, and 1 hour is equal to 60 minutes, and 1 minute is equal to 60 seconds. So now if we look at our units, days cancel, hours cancels, minutes cancels, and the only unit we have left in the denominator is seconds, which is exactly what we want. We do have to fix up our numerator though. And for that, we know that there are 2 pi radians in 1 rotation by definition, right? Because a circle has 2 pi radians in it. And at this point, our conversions are completed. So we have 2 pi in the numerator, divided by 24, divided by 60, divided by 60. And we get a small angular speed, right? 7.27 times 10 to the minus 5 rads per second. So not very fast at all. The other piece of this that we need is our radius. And we need our radius in meters rather than kilometers. So we have to make this note, right? 42,250 kilometers is equal to 42,250,000 meters, which we're going to write as 4.225 times 10 to the 7 meters. Okay. Now that we have both of the pieces of what we need, we can apply our centripetal acceleration formula. And the centripetal acceleration that the satellite experiences is equal to 7.27 times 10 to the minus 5 squared times 4.225 times 10 to the 7. Right, this is in meters. This is in rads per second. And at this point, we go to our calculators. We get something like 0.223. This is quite small, right? Acceleration due to gravity on the Earth is 9.81 meters per second squared. So this is, like 2% g. So 2% g, that's how much gravity you would feel if you were orbiting in a geosynchronous orbit. Any questions on problem 3 before we move on? Okay, no questions. Let's take a look at problem 4. All right, 10-meter long truck is traveling at a constant speed and is overtaking a 3-meter long car traveling at a constant speed. How many seconds elapse between the front of the truck being even with the back of the car and the front of the car being even with the back of the truck? All right, so this one I think is definitely trickier to visualize than it is to actually calculate. So, in fact, for nobody who neglected to draw a picture on the exam got this question right. At least in the ones I've graded so far, which is most of them. So we actually have 2 situations we want to compare. So let's draw a picture for each of them. So we have a truck. All right, let's see. That's enough wheels, I think. No, it's not a steam engine. All right. Clearly, I don't know how to draw trucks. That's okay. It is drawing even to a car which presumably is not in the same lane as the truck. Otherwise, this would be a collision problem instead of a kinematics problem. And yes, that's exactly what cars look like. Don't at me. The length of the truck is 10 meters. The length of the car is 3 meters. We also have the case where the second case that we want to consider is when the truck is actually finished overtaking the car. And for this, I'm just going to draw boxes because I'm embarrassed by my truck drawing abilities. Right here is the 3-meter car. And here is the 10-meter truck. All right. This question alone ate most of my time on the test. Yes. I can see that happening. We're going to call to the right the positive x direction. And now we have to be a little careful with our coordinates. So what I'm going to do, I think, is say that the front of the car at the first instance, that this is where x equals 0. So that means that the position of the car initially is 0. The position of the truck initially is -3. Okay. The velocity of the car is 80 kilometers per hour, but we're going to convert that because we're being asked about something in seconds. And we're given distances here in meters. So let's convert from kilometers per hour to meters per second. So 80 kilometers per hour. 1 hour is 3,600 seconds. 60 times 60. Remember that from the last problem. And 1,000 meters is 1 kilometer. I have people ask me a lot, like, how do you know which of these numbers to put on the top, which of them do you know to put on the bottom? And you arrange them in whatever way will cancel the units that you don't want in your answer. Right? So by putting the kilometers on bottom, we were able to cancel this kilometers. It's in the numerator here, and we're just left with a unit of meters, which is what we were looking for. So our speed then is 80 times 1,000 divided by 3,600. So that's 22.2 meters per second. And we're going to do the same conversion on the truck's velocity as well. Right, so for the truck, it's going to be the 97 kilometers per hour times 1,000 meters per kilometer divided by 3,600 seconds per hour. And so the truck is moving at a speed of about 26.9 meters per second. Okay. We know one more piece of information in this problem, and that is that the difference in position between the difference in position between the car and the truck. So maybe that we'll write that difference between from car to truck is 10 meters, right? So that at our second point in time, the front of the truck is now 10 meters ahead of the front of the car. All right. So now we have enough information to go after what we want. And we've got, also, our accelerations are 0 in both cases. So if we've got distance and velocity, and we want time, that looks like another job for kinematic 2. So we're going to have x equals initial position plus v naught t plus 1/2 at squared. In this case, for both vehicles, the acceleration is 0, so this term goes away. And what we're actually looking at here, right? So if this is time equals 0, and this is just time equals something, we want to work with the difference between these two. So we have the position of the truck minus the position of the car is equal to 10, but that's also equal to the difference in the initial positions minus the velocity of the car or sorry, let me, right, we're doing truck position minus car position. So let's do it all at once, actually. So the truck's position will be the truck's initial position plus the truck's velocity times time, and the car's position, which we are subtracting, will be the car's initial velocity plus the car's velocity times time. And now we can distribute this negative sign and rearrange terms a little bit. So we have the difference in the initial positions plus the difference in the velocities times t. And we can go ahead and solve for t in this case. So we have xt minus xc minus difference in the initial positions, all divided by the difference in the velocities. Difference in the final positions is 10. Difference in the initial positions is -3. And the difference in the velocities is about 4.7. Turn to our calculator. 13 divided by 4.7 gives us about a little under 3 seconds. All right, do we have any questions on problem 4 before we move on?
So here's the thing, right? I got there, I got like the same result, thankfully. I'm not sure how. Well, I am sure how, but it's like I didn't do the exact same process as you. I think I might have broken up the steps into like 2 steps, because what my thinking was for this problem was like after a while what I did was I just kind of had two portions. It was like getting the front of the truck to meet the front of the car, and then getting the time that'll take the truck to clear the rest of the car, where the front of the car is on the back. So basically what I did was I got 2 different equations through the work I did, where I had 2.13 seconds is how long it would take for the truck to clear the car, like for the back of the truck to reach the front of the car. And then I had another one where it was the front of the truck reaching the front of the car. And I just added those 2 together, and somehow I got 2.77.
Yeah, that sounds totally reasonable, actually.
Okay, so so we don't need to follow like the exact same process, right?
No, you don't need to follow the exact same process. There is definitely more than one way to skin a cat. I've been told that that's a dated expression and that I should stop using it, but I don't know of an aphorism that has the same meaning. So for now, I'm going to keep using that. But yeah, there's more than one way to get there. Yeah, you can do everything relative to a stationary car. Like you can say, well, just define the a moving coordinate system. So the velocity of the car is 0, and the velocity of the train or the truck is 4.6. That's perfectly fine as well. Eric says you ended up getting 2.73, also perfectly fine. There's more than one way to get there.
No, I just wanted to make sure, because like again, like I was saying, this problem like destroyed me for a while, because like the other problems, it was like really familiar, and then like I somehow for like problem 5, we'll see, it was a lot like the labs that we did. Like we had a lab pretty recently that was sort of like it, so that somehow helped. Yeah, but yeah, no, this problem was kind of rough.
Yeah, I chose problem 4 specifically because the calculation is simple once you've conceptualized it.
Okay.
Yeah.
All right.
So that yeah, that's by design. Um, so yeah, if you got there, no matter how you got there, full points. Right, as long as you weren't guessing or yeah, you know what I mean. So let's take a look at if there's are there any other questions on this one, or can we go on to problem 5? Let's do problem 5 then. So a diver is exploring a shallow reef off the coast of Belize. She initially swims 90 meters to the north, then turns east and continues for another 200 meters. She then follows a grouper as it swims 30 degrees north of east for 80 meters. All the while, a local current pushes her 150 meters south. Where is she now in relation to where she entered the water? Okay. So in this problem, the picture is almost literally everything. So we have an original position here. Go 90 meters north, and then turn east for 200 meters. And then we go 30 degrees north of east. For a little bit. And then there's also the effect of the current, which, you know, we can just add that on at the end. So then the question is, what is, you know, this total distance from where she started to where she ended up? And even though I've drawn it and it kind of looks like a horizontal line, it's, you know, by no means a horizontal line. Instead, we want to write all of our vectors as components. So our first vector, call that A. It's nothing in the x direction, 90 in the y direction. Although I guess I should then really quickly specify positive y direction is north, positive x direction is east. All right, our second leg of the journey is 200 in the x direction, nothing in the y direction. The third leg of our journey is 80 cosine 30 in the x direction, 80 sine 30 in the y direction. I assume by this point everybody is comfortable breaking up vectors using sines and cosines. If you're not, please call out. We will go over this in more detail. And then our last leg is due to the current pushing us around, and it's 0 in the x direction, and it's minus 150 in the y direction. So what is our total vector, which I'm going to call R here in purple, R for resultant. The x part is going to be 0 plus 200 plus 80 cosine 30 plus 0. The y part is going to be 90 plus 80 sine 30 minus 150. Right. Of course, 80 cosine 30 and 80 sine 30 are just numbers. So cosine of 30 is a half. So this x part is 240. Sine of 30, sorry, Strike that, reverse it. Cosine of 30 is square root of 3 over 2. So our x part is going to be approximately 270-ish. And then our y part, sine of 30 is a half. So we have 90 plus 40, which is 130, minus 150, end up with negative 20. So there's our x and y component, or y components of our final position. The distance from our initial position, we can use the Pythagorean theorem for that. Which is something like 270 meters. And then the angle from, compared to east is going to be tangent inverse of 20 over 270. Wow, little dyslexia going on there. When I'm doing tan inverse, by the way, I almost always just take the absolute value of the components, and then afterward I specify the angle relative to what to put the direction in. So, for example, for this case, 20 over 270 is about 0.07. Tangent inverse of that is about 4 degrees. So 4.2 degrees, and I'm going to specify, right? Note that we have a negative y component, a positive x component. It's going to be in the fourth quadrant. So this is going to be 4.2 degrees south of east. Okay. We have questions on problem 5. Does everyone feel okay about this one? If you stopped the problem here, by the way, and just gave me the components, that's full points. Right? I didn't specify magnitude and direction. I asked just where is she, and specifying it as a vector with x and y components, perfectly okay. So, in fact, if you gave me the components like this and then gave the the distance is about 270 and then didn't specify an angle, I'm still going to count that you gave me the x and y components. Added 180 degrees inputting south of east. So if you put 184 degrees, that's actually in quadrant 3, not in quadrant 4. So that direction is not correct. All right. Any other comments that we want to make on this problem? All right. So this problem 6 is really a math problem. So let's cover this really quick. So when we write c squared, and c is a vector, what we mean by c squared is c dot c. And if c is equal to a plus b, we have to do some foiling, and distribution of multiplication over addition, right? Foiling out binomials works exactly the same with the dot product as it does with simple scalar multiplication. So we get a dot a plus, so that's our first. Our inner is b dot a. Outer is a dot b. And last is b dot b. Notice that b dot a and a dot b are actually the same thing because the dot product is commutative, just like normal scalar multiplication. So these two terms here, we can replace that with 2b dot a. So we and notice that a dot a, well, that's a squared, right? Just by our definition, just what we started up here. If c squared is c dot c, then a dot a is a squared. B dot b is b squared. And then we have 2 b dot a. And one of the nice properties of the dot product that we covered in class is that when you do the dot product of two vectors, you get the magnitude of one times the magnitude of the other times the cosine of the angle between them. And that is exactly what the problem asks you to show. So this is like the law of cosines for dot products. Any questions on problem 6? Whoops. Okay. That's fair.
No, basically what I did was, like, to be real with you, I wasn't exactly sure what I was supposed to be like what was going on. I have something very similar, except what I had was I had a plus b and then times a plus b again.
Yeah.
And well, you got a dot b, right, for the second part, like in the first step, the first line. You got a plus b times a times b again, right?
Yeah, so there's a b times a plus an a times b.
Yeah, so what I did was that second a times b, I actually just made an a plus b again, and
Gotcha.
Oh well.
Tried to use a triangle to justify the question. That you could do it that way, for sure. You could write it as a triangle and use the actual law of cosines. If you remember the law of cosines, that definitely works. All right. Do we have any other comments or questions about the exam? Yeah, there was extra credit, and the extra. I mean, only a few people took advantage of the extra credit, which is unfortunate. So the extra credit. Let's see, how much did I say the extra credit was going to be worth? I haven't actually factored that in yet, but I think it ends up being like an extra 3 points. So like a third of a problem or something like that. Or is it like half a letter grade? Anyway, it's noticeable but not overwhelming.